Welcome back to the office. Today we will continue on our journey through ordinary differential equations, but it'll be good. We'll reap some of the benefits. We've done the hard work, we'll develop some more of the algorithm, and then we'll start applying it. And once we have these tools, we can really solve any problem you want dealing with differential equations. So that's good. So what we'll see is that we'll benefit greatly from having a standard form. We've spoken about that already, and I'll review what we've said before because you may not remember, and I may have forgotten myself. It's been a while. So we'll review the standard form we put all differential equations into, and then once we have that standard form, we have one or two algorithms we use to solve them. So it's a good way to go. What you'll find today is that even though when we solve ordinary differential equations, what we're doing is an integration process, sort of the opposite of a differentiation, the words we use, the techniques, are very similar to what we used when we spoke about derivatives. So if you go back and look at that, if you're having some problems today, you'll see it's the same basic idea. So we'll get on with it. What do we see? Let's look at slide 2. And slide 2 is an old friend of yours. It's the review. What we're trying to look at is forced oscillations. We're trying to solve a physical problem in which we have a mass, m, attached to a spring. Any kind of a spring could be linear, nonlinear, and we'll discuss both. Plus there's some external driving force, this funny shaped hand, pulling it back and forth. So that's a time-dependent, a general problem. So we see equation 1, which is just Newton's second law. That's a second-order differential equation of an ordinary type, no partials. That's what we're trying to solve. Okay, and we know how to put that into standard form from our last lecture, and we see that standard form always has the form of equation 2. And let's look carefully at equation 2 again. It says we always write ordinary differential equations as a first order, just linear, first time derivative, dy by dt, just first derivative in time, of some vector, and that's that little arrow on top. Okay, the little arrow means this is a vector. It has a number of components. If this was a book, we'd put it in bold print, but you can't see on the slides bold very well, so we're using an arrow here. So that's arrow means this can have multiple components. F is the derivative function. It's just some function we need to know to solve the differential equation. So equation 1 here and equation 2 have to be made the same. And we've done that, put it into standard form in equation 3 and 4. So we define, as we normally do, the first, which in computer science talk becomes the zeroth component of the unknown y, is equal to the position x of t. And the second component, or the 1 component, is called the actual velocity, which is the derivative of the first component. So when we've done that, the differential equation we want to solve, equation 1, becomes equations 5 and 6 here. So we have simultaneous equations. We have the derivative of position is just what we call velocity, y1. The derivative of velocity is just acceleration, and that's what we have in equation 1. So we just repeat the right-hand side is 1 over m times the force. So in the standard form, we now have the force function f0 we need in equations 7 and 8. Its first component, its zeroth component is y1, and its 1 component is the force. So that's a review. That's the equations we want to solve. So let's take a look now at slide number 3. So slide number 3 is our first introduction to an algorithm, a rule, an approach, a viewpoint of how you go about solving differential equations. And we'll use a standard technique, and it's known as leapfrogging or time stepping. Okay? And what we're trying to do here is we say we don't have to solve the differential equation from A to B, even though that may be your assignment. We have some starting time. We need to know what the solution is 1,000 years from now. Well, that's hard to do. What we'll try to do is solve it in steps. Small steps that take us from the initial time 0 or A to the final time or B. So this is called time stepping, and it's just an integration technique, step-by-step integration, and it's also called the leapfrog technique. And of course, if you remember your classes on ordinary differential equations, you'll remember that the solution of a differential equation requires you to have a complete set of initial conditions. So the solution we're talking about here is always taking the initial conditions at one time. They could be the initial position and maybe the initial velocity for a second order equation, and then carrying that forward in time. So this leapfrog technique is very much like a castle built on sand, because we start off with something known and we continue it through all time to very long times, and we're extrapolating. Good scientists interpolate, predictors of the future extrapolate, and that's what we're trying to do. So in present day terms, one of the arguments about global warming is how much is caused by any one effect. And it may seem obvious to you what is the answer, but to prove that mathematically and scientifically requires you to solve differential equations, much more complicated than any of the ones we'll show here, requires you to solve these differential equations from present known conditions and extrapolate that forward hundreds of years maybe. Well, that's hard to do. These time-stepping methods are built on sand. The errors can accumulate. If the errors keep accumulating, you end up with garbage. But they work. We'll see how well they work very soon. So what do we do? So we start off at time A. We'll call that time 0. Okay? And we'll say the initial solution y is known at time 0. Okay? And this can be used for any dependent and independent variable names. We'll just call it time stepping. Time is the, which one? The dependent variable. No, it's the independent, because we can change time any way we want, so it's independent. We can say, let's look at the solution at 12 hours from now, and y is the dependent variable. Okay? So, but we'll call it time, and we won't use those dependent, independent. They always confuse me. So we start off with some initial condition, and we want to solve not for some later time b, at least not initially. The whole algorithm does one thing. It just takes this initial condition and it moves it forward one very small time step. And we call that time step h. We keep it uniform, at least to start with, and it has to be a small number. What is a small number? Well, if the world changes day by day, then some small fraction of a day is a small number. If you're talking about a proton zipping by another proton, that only takes 10 to the minus 23rd of a second, so it has to be a small number compared to that. So whatever sets the time scale of your problem, we need a small number. And we need to get then, by being clever and using some mathematics, from the initial time to the next time. So we move forward one step at a time. How do we do that? Well, we do that by knowing the derivative function f. So if you recall our standard form, it always had a right-hand side with a function f. That's all the information we need. So we take the derivative function as known initially, and we use that to extrapolate the solution forward one time. Once we have that, we have the solution at step 1. Then what do we do? But then we stop thinking. Then we just say, well, if it was good enough to get me from 0 to 1, it better be good enough to get me from 1 to 2. And then I just use the values I had at time 1 as new initial conditions, and I move ahead. And that's how it works. And I just keep stepping ahead, and I just quit when I'm done. I'll quit when I end up with a final velocity that I want. Okay? And let's say here, to be careful, we're using the subscript, that's the one down below, to indicate different time steps, y0, y1, y3. We will use the superscript up above, which we did on the previous transparency already, to indicate components. So the 0th component being position, the 1 component being velocity. So we'll use both super and subscripts, but not on this slide. We'll wait till the next slide. Okay? So how accurate a method is this? Well, that's for you to figure out. But we can give you a hint. If you keep h small, then accuracy is good. So we have to keep h small. How small? Well, if you keep making h smaller and smaller until you get good accuracy, at some point you'll require so many steps to get from A to B that round-off error comes in. So there's always a balance. You'd like an algorithm which lets you use small h but doesn't require you to use minuscule h, because then you have to make too many steps. And how do you choose h? So if we look at the bottom here of slide number 3, we see a graph, and that's an interesting graph. We made it up ourselves, and you can see here's a signal, and it's slowly varying at first, then it's largely faster varying, then it becomes even more rapidly varying. And what you want to do is to say, okay, we want maybe for small times here we want to use a large value of h, maybe for middle times a somewhat bigger value, smaller value of h rather, and then for very large times even a smaller value of h. And so the rule of thumb is roughly, in my mind anyway, you sort of want to have 100 to start with, at least 100 time steps in any typical time scale. So if you have one period for an oscillator, you should have at least 100 time steps to get good accuracy. Okay. Then you probably want to go beyond that, but at least to start off with, that's a good place to start. Okay, 100, 1,000 is not unusual to get good accuracy, but that's the rule of thumb. Have you ever heard the expression rule of thumb? Well, it's an interesting historical perspective. Some people claim that it came about because a man at one point was permitted to beat his wife by English law with a club or a piece of wood which was thinner than his thumb. That's sort of been discredited. That's probably only true in the last 200 years. There's earlier references to the term, and it came about in some ways because the king had a thumb which was an inch, and that was the rule that set the measurements. Okay. Others have said that a czar once put his thumb down on a map saying, this is where I want the railroad to go, and the line became a thumb-shaped line. So it's an interesting term. We'll use the rule of thumb to remind you we mean 100. Okay, so let's look at slide number 4, our first algorithm. So the first algorithm we'll discuss is called Euler's rule, or Euler's algorithm, and it's much too simple. And yet, it's going to be used all the time, even in the most sophisticated procedures. And the reason is, we need it sometimes to get started. And we'll see. The algorithm geometrically says, here's our function y as a function of t, and essentially all we're trying to do is integrate that function, find the area under the curve for one small interval of width h. Euler's rule says, let's start off with a tangent, straight line, to the curve at time 0 when we start, and use the area under that triangle as our solution. So this you recognize as just the trapezoid rule we've discussed already. Okay. So, but here we now have to redo the trapezoid rule into, new language. Okay. So when we talk about integration rules, let's continue thinking of time. I'll assume you've had first year physics. And we'll look now at just the equations of projectile motion, the bottom here of the slide, lower right-hand corner. In first year physics, if you look at those equations for time t equals h, the time step, we know that the initial position comes in, the initial velocity comes in, and so the position at h, time h, is going to be the initial position plus the initial velocity times time plus 1/2 the acceleration, often due to gravity, times h squared. So this is what we call, in applied mathematics, this is a second order algorithm, because it has the first order time and has the second order time occurring there. That's just the acceleration. The velocity, which changes simultaneously, is just equal to the initial velocity plus the acceleration times the time. So for the velocity, it's a linear algorithm, but for the position, it's quadratic. And if you recall, this is really the standard form for our differential equation. We have a velocity and we have a position. So we'd like to have an algorithm that's at least as good as first year physics, because anybody can take first year physics. Okay? So what's our algorithm? Our algorithm is where we have a linear algorithm. Linear in what? In time. We're extrapolating forward, which again is an area you're not supposed to do. There could be problems. What are the problems when you extrapolate? There could be errors. Okay, so what we see here now on the slide is equation 1. Equation 1 is just the equation we like to solve. That's our standard form for a differential equation. Says the change in the position y as a function of time is equal to some derivative function. Okay. If we approximate, this is Euler's rule, if we approximate the derivative as just the change in the position of one interval divided by the width of the interval h, and that's going to be equal to, and here's the careful part, it's going to be equal to the derivative function evaluated at a time at the beginning of the interval. That's Euler's rule. Okay. So here, to go ahead from step n to n plus 1, we take the derivative at the beginning of the interval, which means the tangent here, the straight line, and we continue it. So on equation 3, we actually have the algorithm. The algorithm says the solution at any time n plus 1, and this could be all the components simultaneously. So even though it's simple, it solves everything simultaneously, and computers love to do that, you don't have to, is equal to the solution at the previous time n plus h, the step size, times this derivative function evaluated at the initial conditions. So the algorithm is 3, and if you notice, well, it's very similar to what we'd say for elementary physics for the velocity, but this is just linear in time. So whereas a better answer would have a quadratic term. So this algorithm has an error, as we indicate here at the bottom of equation 3. It has an error that goes like h squared, because we're leaving off effectively the acceleration term. So if h is made small enough, this is just the real world, this is good old physics again. If h is made small enough, positions change mainly because items have velocity, not because they have acceleration, and the velocities change because items have acceleration. But if h gets a little larger, you need the effects of both. So this is our algorithm. It's not terribly good, but it's self-starting. So if you remember, we're trying to integrate out from initial time. This lets us get going. Once we get going, then we can improve the algorithm. And on slide 5, we talk about better algorithms. So take a look. So there's a whole collection of, 3 maybe we'll talk about, whole collection of algorithms called Runge-Kutta algorithms, 2 names with a dash, and they're a better way of approaching this problem, more uniform, and you could make them higher and higher accuracy. And we'll talk about mainly RK2. So we'll talk about a second order method, because that's about as complicated situation that I can talk to you about here without getting hopelessly confused with the algebra. But we recommend you always use higher order yet, RK4. So RK4 is particularly the accepted now standard for industrial strength algorithms. If you want, we'll also talk about RK45, which is RK4 with adaptive step size. So this is a case where the computer is smart enough to give you different size steps depending on how rapidly the function changes. And as we'll see here, while we're still extrapolating the initial condition forward in time, we're using interpolation techniques. So if we look now at slide number 5, we see 3 equations in the left here. And what are they? The 3 equations say, here is equation 1 is the problem we're trying to solve. We want to integrate a differential equation. Equation 2 gives you the formal solution, no approximations. We love it. Okay? So y of t is just the integral of f over time. That's an indefinite integral. If we want to calculate how much the solution changes from step y sub n to step y to the n plus 1, one small step at a time, we can just perform the integration from time t sub n to time t sub n plus 1. Okay? So this is the exact solution. And what the Runge-Kutta technique says is, okay, we need to evaluate the integral here in some approximate way, and let's look at our picture. Rather than using the slope or the value of the function at the beginning, we'll make all our expansions about the midpoint. And that's the trick. So rather than using the initial slope, we'll take the slope in the middle. That'll still be as small amount of work as Euler, it'll just give us a better approximation. So if we take, look at the picture, if we take the slope in the middle here, which I've drawn on this line here, it's the same as right above, move it forward, okay, and use that to extrapolate, we get, these two are pretty much parallel, we get a straight line forward, and what you see here is the error is relatively small. You know, where the errors were big on the previous slide, the Euler's rule, now the error is much smaller. And in fact, for the same number of evaluations, this always gives us one order higher precision. And let's see that, but you can see that in the graph, okay? So, what we'll define here is n plus, just because I don't have enough room on the slides to write n plus a half every place. Okay, so n plus means half step to the middle of the interval, and the Runge-Kutta technique now says we need to approximate the derivative really in the middle of the interval. So we take the value of the function f, the derivative function, as its value in the middle, plus a Taylor expansion, and the different levels of RK algorithm just correspond to how many terms you keep in the Taylor expansion. So we'll keep the first term here, or the second term, first term in T, if you want. RK4 keeps another 2 terms, and that's all we'll ever worry about. Okay? So this is the approximation. We say let's evaluate the function at the middle, the midpoint of the interval, and then we're expanding. So it's time T minus the midpoint times the derivative evaluated at the midpoint. What's the big thing here? Why am I making such a big fuss about this? Well, the reason is because once you start at the middle of the interval, half of the time steps will be smaller, and the other half of the time steps will be larger than the middle of the interval, and the terms linear or cubic or fifth power in them will always cancel when we do the integration. And that's the trick. Okay? So it's like when we did derivatives, remember how central difference always worked better than forward difference? Same thing here. We'll set up the algorithm, this is how applied mathematicians do it, we'll set up the algorithm to get automatic cancellation of the next order term. So for no more work, we get better precision. So now, the upper right-hand side of this slide, we do the integration. We just say the integral from n to n plus 1 is approximately the value in the middle, that's the constant, times h, the time step. That's it. That's Euler's algorithm. And so the algorithm says to move ahead a step, we just take h as before, and we evaluate the function in the middle. But it's h cubed. The h squared terms automatically cancel when we do the integration. Sounds too good to be true. It is. Okay. So if we look here at the next slide, slide number 6, we see how do we actually apply this algorithm, and that's where the problems come about. Okay? So equation 1, look at that, is our algorithm. Can you remember that from the last slide? Hasn't changed. Okay? So that says to move ahead one step, we take the step size h, evaluate the derivatives in the middle of the interval. Okay? How do we evaluate the derivatives in the middle of the interval? Well, if you think of it, the time is easy. Time is just says h over 2. That's half a time step. But this requires us to know the solution that we're looking for, which we don't know, which we need an algorithm for in order to evaluate the function in the middle. And that's the catch. Okay? It's a great algorithm if you know the answer, but if you don't know the answer, it's hard. That's where Euler comes in. So even though this is a better algorithm, we'll use Euler's algorithms, Euler's simple-minded method, to give us an approximation for the middle of the interval, and since we still get an h multiplier here, it actually comes out to be a higher order algorithm. Okay? So this is Euler's now being used here. So we'll evaluate the unknown solution at the midpoint as the solution at the beginning of the interval, plus the derivative times h over 2 because we're just half a time step away. And now we have to evaluate the derivative using the Euler's rule, so it's the initial values of the function. So that's just to give us the value of the function at the midpoint of the interval, which we need in order to determine the derivative at the midpoint. Once we have that, then we'll use Runge-Kutta. That's a lot of words for what is really pretty simple. So on equations 4 to 6 here, we put the pieces together. And we use the, again, standard techniques. We'll say the full vector, in other words, all components, are brought forward one time step by adding a correction. Gradients, as they're called, these k terms. K2. K2 is just h, which we know, the derivative function, which we know the right-hand side of the equation, but it's evaluated at h over 2 forward in time, and then it's evaluated at the known value of our solution at the beginning of the interval, plus some other k, some other gradient over 2. Okay? This just follows from Taylor's expansion. And k1 is just h, this is where Euler's rule came in, times the derivative at the beginning of the interval, and that there we knew the solution, we knew everything. So we're fine. So this is our rule. Okay? So let's apply it. We say it's a simple rule. Now let's apply it to a spring, our old friend. So on the right-hand box here of equation slide 6, we'll apply the rule. And what we see is, first, that it tells us now we have both components. Okay? So we're starting off with a 0 here as the initial time values. We move it to 1. So that's time stepping. We have a superscript 0, which means we're talking about the position, not the velocity. So we're saying the initial position moves ahead one time step by adding in h times the derivatives evaluated as the prescription says, and when we substitute in what the f value is, we get the initial position plus h times initial velocity, the same as elementary physics, and now we get an h squared term. That's what we're looking for. So it's you're thinking he must be crazy to get excited about that, but now we're at least as good as elementary physics because we have the h squared term. And if we do the same for the velocity, that's going to be easy to work out. We get the velocity has the linear term, that's all there is, times the force function evaluated someplace in the middle, and there's the h term. Okay, so this is our algorithm. This is RK2. We now need to extend this forward to RK4. So let's look now at this slide again, review it, rest your eyes, and then we'll move ahead. Well, it's a complicated looking slide, but you'll understand it better once you apply it. Let's look now at how we generalize this method to 2 higher orders. And the answer is, I won't force you to do it. How about 4th order Runge-Kutta? Obviously, it's the same idea. The idea here, though, is we have our function, we want to integrate it, and we'll still work around the midpoint. But now we'll expand the function up to order 3 in time, or in h, around the midpoint. So we have a 4th order, we have a 3rd order cubic expansion of the function, and cubic expansions are very good. The error goes like order 4, and that's why it's called RK4. It's good up to 4th order in precision. So this method, RK4, is generally considered an excellent balance between power, it works on most everything, it's very precise, and it's still very simple. Maybe not that simple to derive the first time and get all the halves and the thirds and the quarters right, but it's simple to program up. Nevertheless, we recommend, at least for beginners, use our program for RK4 rather than write your own to start with. Because if you make a little mistake, you may end up with a very good answer, but not quite as good as it should be. So if those of you who are good programmers, take that as a challenge. See if you can write a better one. Okay? But at least to start with, that's what we'll do. Okay. So what's the method? So the method here is given on equations 1 to 3. And it's the same idea. We're just expanding in a Taylor series around the midpoint. So we'll end up with h to the 5th terms that have an error, because all even term errors have canceled out when we do the integration. So the solution looks the same as before. It's equation 1 here. Equation 1 just says take the initial value, beginning of the interval, you move it ahead one time step by adding together 4 gradient terms, and these funny factors, 1/6, there should be here's a half, they just come about because of Taylor's expansion. So, and what we see here is each k corresponds to higher and higher order as they work through in powers of h. So it's more and more precise. That's our algorithm. And if we look at the last correction here, so, this is for h squared, h cubed, this is the h to the fourth term, correction. Okay. So what we see here is K4 has an h out in front. We then evaluate the right-hand side. So the right-hand side is the derivative function. The derivative function is your subroutine. So that's the subroutine you have to write. So if you're sitting here looking at this and saying, I don't want to program this up, we don't want you to program this up. We don't want you to get your dirty little hands in our beautiful algorithm. Don't touch it. Okay? All you program up is the function. Okay? The right-hand side, the derivative function. And what we have here in K4 is your derivative function evaluated at some middle position, y sub n plus K3. Okay, what is K3? Well, K3 goes like h, so there's a power of h. It has K2. K2, if you go, there's an h. It has another K1. K1 goes like h. So the K3 term is an order h cubed correction. We multiply by h, we end up with h to the fourth accuracy. So that's why this is called RK4. It has 4 powers of h. That's very good. Okay, so we're fitting fourth power. So we have essentially not a cubic, that's a quadratic term. Not a quartic term, powers, quartic polynomial, fourth degree polynomial we're fitting the function to. And that's very good when you make h small. So, we've done enough now. I think you need to take a break and you need to start applying this someplace real. So, we'll meet you in lab. We'll go there next. Take care.